calibrated. Okay, so now let's move on to something slightly different and talk about vectors. Unless anybody has any questions about sig figs or units. No? Okay. All right, so if it's been a while, make sure you remember your trigonometry. Right? So for a triangle containing 90 degrees, a 90-degree right angle, recall that maybe in high school you learned SOHCAHTOA. Sine is opposite over hypotenuse. So if you're looking for this angle, the sine of this angle is the opposite edge, this y here, divided by the hypotenuse of the triangle, which is, in this case, labeled r. The cosine is the adjacent over the hypotenuse, so that would be x, the adjacent bar to this angle, over the hypotenuse. And then the tangent is the rise over the run, right? So opposite over adjacent. And if you know x and y separately, then the hypotenuse is given by Pythagorean's theorem. R squared is equal to x squared plus y squared, right? And then you can take the square root of this to get r. Okay, and then the only other thing that you should be aware of that hopefully you've done at some point in your math career is on your calculators there's an inverse button. So that allows you to take the inverse tangent or arctangent. Right? So if you are trying to solve an equation like, I know what r is, but I'm trying to get what x is, right? And you know the angle. Like I say, I have something that has an r of 10, and it's got this angle, like in that problem that we just did, they may give you the angle is 30 degrees, and you want to know maybe how far it went in the x direction. Right? So you may have to take like an arc sine or arc cosine. You basically say, well, if I want to get the angle out, if they don't give you the angle, then what I can do is I can take the inverse cosine of this number, this fraction, and get the angle out. Okay? So make sure you know how to do all those things on your calculator. All right. So with that as background, let's now talk about vector addition. All right, so vectors in general. Did I define what a vector is last time? No? Okay, so let me talk just about what a vector is. So first of all, how many of you feel comfortable with vectors? You've done enough math that you feel somewhat comfortable with vectors. Only about a third of you. And how many of you have just never even heard of vectors before in a classroom? Okay, so there are some of you. So excuse me for going a little bit maybe redundantly slow, but there are people who need it. So vector sounds like a scary word, especially because you look in course catalogs and there's terms like vector calculus books and stuff. But we're not going to do vector calculus. We're not going to do anything complicated with vectors. Vectors are really very easy. Right? Vectors are how you get to a restaurant. That's all it is. It's a map direction. Right? A lot of the numbers that we deal with are just numbers. Right? If I ask you the temperature in this room, you might say, temperature is 72 Fahrenheit. Right? If I ask you how many eggs there are in the carton, you say there's 12. Unless you drop one, then there's 11. But there's no direction involved in that. It's just a number. Right? But if I ask you how to get to a restaurant, right, and you come back and you tell me, okay, what you want to do is you want to drive 1 mile, and then drive 3 more miles, and then drive 5 miles, right? And you're there, right? You'd be like, you are the worst person at giving directions, right? Because that tells you nothing about how to get to the restaurant. Yes, you do have to drive 1, 3, and 5, but if you don't tell me what direction to go, that's pointless, right? So you might tell me, go 5 miles east, then go 1 mile north, right? And then you may actually go kitty corner across an empty lot, right? At 45 degrees across the empty lot. That will get you to the restaurant you want to go to, okay? So those numbers are meaningless unless they have a direction attached to them, and that's what a vector is. It's just a pair of numbers, a distance or a magnitude, more generally, right? But for directions, it's a distance, and an angle, right? East is an angle, right? It happens to be 0 degrees along the x-axis. North is 90 degrees compared to that x-axis. Going back west would be 180 degrees, right? And that's all vectors are, right? So if we want to do things like tell somebody how to get somewhere, because we can either go as the crow flies and just say, well, it's exactly 40 miles at 37 degrees, and you're just going to have to walk through walls, to get there, right? That's fine if you're a crow. As the crow flies, you can fly straight there. But most of us have to go around things, right? So then you might give directions as a set of go this, then go this, go that. And if I then ask, okay, so how far am I away from where I started as the crow flies, right? If I went 5 miles north and then 3 miles east and then 45 degrees by 2 miles, where did I end up compared to where I started if I look at my GPS, right? So how do we answer that type of question, right? And obviously, I'm giving the most intuitive version of this, right? But I'm not here to teach you guys how to get to restaurants, right? This is just a easy way to understand how to vectors add. And then when we start talking about forces that also have a direction, because if I push on something, it matters whether I push it, like I said, whether I push it this way or I push it that way, because there's very different effects. Hopefully nobody wanted that. So because directions matter with forces as well, and they add the exact same way. Okay, so the rules are this. There's two methods we're going to talk about. We're going to talk about a graphical method that you never really use, right? Maybe in lab class they ask you to do it one time and actually measure the result, but most of us don't do that, right? We're going to use the algebraic method. The reason we teach you this anyways, even though we never actually sit there and use it to measure stuff, is it's a great cross-check, right? Because if you add a whole bunch of vectors together with the math method, you'll see that it can be a lot of minus signs and plus signs, and you can easily, I'm always dropping minus signs, right? So when you get to the final answer, it's just like, well, I don't know if this is the right answer, it's just what the math said, right? But if you can kind of do this pictorially on paper or even in your head and say, well, by the time I add these up, I should be going that way. It should be a pretty big vector, right? If you end up with a very, very small number compared to the numbers you started with, or it ends up pointing that way, then you might want to go back and check your math. Okay, so the idea is that you place if you want to add these two vectors, right? If the directions are go northeast by a certain distance and then go northwest by a slightly different distance, right? Where do I end up compared to where I started? Well, what I do is you put the tail of the second vector at the head of the first arrow, right? We represent these things as arrows. The length tells you how far or how big the force is or how big the travel is, and the angle is obviously give the direction. Okay, so we can slide this around. We bring this guy so that its tail touches the head of this vector, right? And then, and in doing so, what you're allowed to do is you're allowed to translate the vectors. That means you can slide them around, right? So I can take, let's see, if I have one going this way, and I have one going this way, right? I'm allowed to, oh. Sorry. My kids lose a pool noodle every year. All right, so we have this and this, right? And I can slide these around. If I start with this, let me straighten that out. Okay, if I'm allowed to do all of this, and these vectors are still the same vector, right? It's still a vector that's this long pointing at this angle. So I'll bring this up to here, and then the resultant vector, which I don't have a black pool noodle, will point from the beginning of your travel to the very, very end of the travel, right? So if you do it correctly, you'll get this. But if you do it, when you do it, you are allowed to slide these guys around the appropriate way, but you're not allowed to rotate them, okay? Any rotation changes the actual thing that the actual map direction, right? So you may not rotate either vector. You may not resize them, right? You can't suddenly take this one and make it twice as long and turn it into this, right? Because then you'll get to the wrong restaurant, clearly, right? And the resulting vector, R, points from the tail of the first vector to the head of the last vector, right? In this case, there's only two. But I could have, if I had a third set of instructions, I could have said, now you go and head 2 miles north. I could have taken the third vector, slid it so that the tail is here, let it point up, and then my resultant vector would have pointed from here to here, all right? And that's all there is to it. Give you a couple more examples. Right? If you had just a straight north and a straight east, right, then the resultant vector just points like that. If you have them in a line, you just keep them in a line, right? A and B, and the resultant vector is the full length. But what if we wanted to do something like, okay, so I've drawn them. Yeah, so here I just drew them a little bit offset. They should, of course, actually be right on top of each other. And where's my minus sign? Multiplication, okay. So I think these are slightly out of order. I apologize. I think this should have come first. So a vector is a quantity that's represented by just a magnitude. Scalar is a quantity that's just represented by magnitude. So when I talked about temperature, when I talked about the number of something, or that's just or even time, right? 3 seconds. Time has no direction. Right? Some might say it only goes forward, but that's not what we mean. Time is just 3 seconds. It doesn't point left, right, east, west. So these are all examples of scalar quantities that we will encounter this quarter. Time, mass, energy, work. It's okay if you don't know what half of these mean. That's what we're here for. By the end of the quarter, you will. But there are also a number of vector quantities. But here you can see that this points to one of the unfortunate drawbacks of physics being such a all-encompassing field, is that there are more concepts in physics than there are letters in the alphabet. And so we end up with a lot of things where the same letter represents 2 different things, and you have to know the context. Okay, so just be forewarned. Okay, but then there's vector quantities that have direction, and I already talked about this because the slides were out of order. I apologize. But the vector quantities that we're going to deal with in this quarter are things like a displacement, a velocity, an acceleration, force, momentum, and torque. Torque is a kind of a rotational force. And don't worry, you don't need to memorize this list right now, right? We'll cover all these and again, I think people came up and asked me, because I know many of you are used to taking biology classes. I'm not big on definitions in this class. So I define stuff for you because you need to have stuff defined for you. But my test will not be, which of these is the appropriate definition for this. Unless it's like a key concept that really, I want to make sure you understand the concept. But I'm not going to, for instance, I'll say this right now. If it was on my last year's quiz, I'll take it off because I rewrite all the quizzes anyways. I'm not going to ask you, what's the definition of accuracy versus precision? That's more of a lab question, right? I want you to understand the concepts and not worry about memorizing definitions. Okay, so this way so we've already talked about addition of vectors, and then this should have been the next slide after that, which would have been the different ways to multiply vectors, right? So this quarter we're going to look at 3 different ways to multiply vectors. Right? The first is easy. It's taking what's called a scalar product. And again, don't worry about the name. It's just taking a number and timesing it by a vector, right? And one way of thinking about that is just making something longer. When you multiply a vector by a scalar, the result is either just the same vector that's larger or the same vector that's now smaller, right? You cannot rotate something by multiplying it by a vector or by a scalar. It points along the same line as the original one, right? If it's a positive scalar, it'll point in the exact same direction, right? So you'll point like this. And if it's a negative scalar, like if you multiply by -2, the only thing is it then flips around and points in the opposite direction, but still along the same line, right? We didn't have to rotate the vector. We just flipped it over. So flipping it over is allowed when there's a minus sign, but only when there's a minus sign. Okay, and obviously if the number is bigger than 1, it turns into a bigger vector. If it's less than 1, it becomes a smaller vector. And if it's negative, it flips around and then also rescales accordingly. There are 2 other ways of multiplying vectors. One we will get to when we talk about the forces in chapter 6, when we get to work. And the other one is the cross product, which we won't get to until chapter 9 when we talk about torque. Right? And we'll introduce them later rather than now. So for now, just remember that multiplying rescales if you multiply by a number. Subtraction is just addition with a negative sign, right? You guys know from basic math that 7 minus 4 is exactly the same thing as 7 plus -4, right? Both give you 3. So that logic holds for vectors as well, right? So if you have a situation where you have to take vector B and subtract it from vector A, and with the math that you do, you will eventually come to a mathematical situation where you have to do this to solve for something, right? And if you want to be able to figure out how to depict this graphically so that you can make sure that you get the right answer, the trick is to view it as A plus minus B. Right? And just on the last slide, I told you that if you put a minus sign in front of something, you just flip it over 180 degrees. Right? Instead of this, it now becomes, oh, I have a way to do this. OK, now it has a direction. Right? Instead of this, it becomes this. All right? So then we can do addition. Right? I took what was supposed to be, if I want to subtract, take A and subtract B, then what I do is I take A without rotating it, B without rotating it, but I flip it over to make it minus B, and then I just add them together. Slide the minus B so that the tail is at the head of A, and the resultant vector now points from here to here. Right? And the other two examples that I had previously, but now I'm going to subtract instead of add B. Yes, sir. Let's go back and look. Okay. Here you see that taking A and subtracting B gave you something with that was a arrow about half the size of B and pointing to the left. Right? Let's see if I was smart enough to use the exact same arrows in the previous example. Right? Here it's not. It's pointing to the right, and it's bigger than both of them. In fact, it's the sum of the two. Right? So you do get different answers. And again, looking at when they were off at weird angles, they can be substantially different. This one was pointing like that. And by the time you get to here, it's pointing straight to the right. Okay. All right, any questions on this? It's not hard, but it is foreign, right? And anything foreign can be hard at first. But play around with it a little bit, and it's not so deep.
For addition, does it matter which thing you put on which edge?
Good question. Does it? So in mathy speak, you're asking if vector addition is associative, right? I think that's like whether you can flip it around. And the answer is it is. It's both commutative and associative. So A vector plus B vector is the same as B vector plus, sorry, bad use of board, A, right? And the easy way to think about that is if I go 2 blocks north, 2 blocks east, and then 2 blocks north, and my friend goes 2 blocks north and then 2 blocks east, we'll end up in the same place. You asked that question, right? And you can try that. And if you're not familiar with vectors, take all of these examples and work them out B plus A and convince yourself that you end up with the same resultant vector. On the other hand, subtraction does not commute or associate. I forget which one it is, right? So B minus 7 minus 4 is not the same as 4 minus 7, right? OK, so now let's take a look at how to deal with these guys algebraically, right? So what we're going to do is we're going to take any vector, and we're going to define a coordinate system. And for the majority of what we're going to do in this quarter, we're going to use the Cartesian coordinate system, just x, y, and z, right? X will point to the right of the room typically. Y will point up. And if there is a z, it's pointing out of the screen towards you guys. Okay? For most things, we'll deal with just x and y. So let's go ahead and say we have a vector that's pointing somewhere in the plane of this board. And I'm going to assume that we have an x and y axis. And we want to determine the angle that this vector makes with respect to one of these axes. And our standard convention is to make the x-axis, the thing that we make our angle. Positive x-axis is what we measure our angle with respect to. And we're going to find the x component of that vector using SOHCAHTOA, right? Right? We said before cosine is adjacent. So we make kind of a right triangle out of this, right? And then how far it goes east, which is the x, is this line, which is the adjacent. And we're interested in how big that is compared to the actual size of the vector, which is the hypotenuse. So adjacent over hypotenuse is the cosine. Right? Cosine is x over r. And we just manipulate these equations to say x is equal to r cosine theta. And if we're interested in the y component, or how far north we end up traveling, we just take the sine. Right? Sine is opposite over hypotenuse, so that's y over r, which gives us y is equal to r sine theta. And so then in vector component speak, we're saying that the x component, how far we traveled this way, when we've actually gone this path, how far along the map east we've gone is just a cosine theta, and how far north we've traveled is a y, or a sine theta. So we take a vector, and we break it into a component along the x and a component along the y. Right? In map speak, I've traveled a certain distance as the crow flies, and I can say that that's equivalent to having gone a certain number of blocks east and a certain number of blocks north to get me to the same place. So I'm just breaking it into purely north steps and purely east-west steps. Okay? So now that we have these two numbers, right? I've taken something, yeah. Is so the magnitude of the vector, we put it in these absolute values to make it always positive, right? And the way we deal with something that would have been negative, it was we just say that the angle, if we wanted this to be negative, right, having a positive vector at this angle, and then saying, well, what if I wanted a negative vector at that angle, right? Well, I could write it that way, or I could say, let's keep the magnitude positive and claim that instead of 30 degrees, it's 30 plus 180, right? We make the angle be the one that tells us whether it's this way or that way, and we keep the magnitude positive. That's the convention. It's a very good question. Okay, so what we've done is we've broken these things into perpendicular components. And this is a very key point that will come up over and over again, is that perpendicular components, what's special about x and y instead of any other random choices, is that perpendicular components are independent, right? So doesn't matter, if I start moving in this direction, right, how far this travel has taken me to the east is independent of how far it's taken me to the north, right? Whereas if I drew my components, do I have that? I have another slide that, imagine that you were trying to give directions for how to hang a picture, right? You want to get it nice, just perfect, and we want the picture to be hung right here. And so right now we've got it right here, and so your significant other says, no, it's not quite right. Move it a little to the right, and then move it up, right? That's great, because we move it to the right. Oh, look, it's perfectly underneath it, now move it up. That works. Imagine if we were in some weird bizarro world where everybody gave directions not in perpendicular components, but along two axes like this, right? Along east and northeast, right? So now we want to get it here, and she says, oh, it's perfect along this axis, right? Now, slide it along this axis. It's not quite right here, so we're going to slide it along this, and I end up over here. It's like, now it's not right this way, so now we got to move it back this way. It's right? How far I move it along this axis changes how far it is on this axis, right? If I move it anywhere along here, it was perfect this here, but now it actually slides over because this thing and this thing are not independent. But when you choose two axes that are 90 degrees apart, if I slide this guy, if my wife decides that she's not happy with the height, it doesn't change where it is left and right. That's what we mean by orthogonal components are independent, right? And that will work with forces and everything else that we deal with. Okay, so we break these up into an x and a y component, and we can deal with those components independently, right? If I say, actually move it a little bit more to the right, all that's going to change is how far to the right it does. It's not going to change how far to the north it is. So when we start adding things, we can add the components independently. So now we've broken it down from this weird idea of a length and an angle, which we're not very used to thinking about. Remember, that's two numbers, right? So it's characterized by two numbers, a length and an angle, right? All I've done is I've translated into a different set of two numbers. I've translated into an x and a y, okay? So I still describe it with two numbers, but now I've got an x component and a y component. So now I've got two numbers without having to deal with direction, but it's still a directional quantity. So I have to have some way of labeling what directions those numbers mean, are associated with. And that's what we get to unit vectors. So unit vector is just a kind of a labeling vector that tells us which directions we were sliding stuff along, okay? So typically we use the directions of x, y, and z, though eventually we might do some slightly weirder things when we get to circular motion. But for now, let's think about x, y, and z. And because we use the symbols x, y, and z in formulas so much, right, we don't want to have the x representing the number and then an x hat or an x vector representing the direction. So they choose I, j, and k for x, y, and z. Okay? That's actually to keep things less confusing, not more confusing. So I hat points along the x-axis, the positive x-axis points that way. J hat points this way, and z hat points that way. K hat, sorry. K hat points along the positive z-axis. So now, when I broke this thing down into an x and y component, I can just report these two numbers, 4 and 3, right? And by putting this little I hat in front of it, what I'm really saying is 4 east and 3 north. Okay, so you can think of these as kind of like east and north labels. If I want to get the angle back, right, I've just showed you how to convert from, if I tell you how long it is and what angle it's at, and we want to convert it to an x and a y component, I just told you how to do that, right? We should be able to convert back, right? Translate from English to French and back from French to English, right? So if you have the components and you want the angle, you just take the arc tangent of this, right? Tangent of this is y over ax. So the inverse tangent will give you the angle back. So inverse tangent of this ratio. And that's here, right? So this ratio is 0.75. So inverse tangent of that will give you 36.9 degrees back. So now I have the angle, and if I remember the other way of representing it was angle and magnitude. So for magnitude, I just used Pythagorean's theorem, right? Because I chose nice, convenient x and y coordinate systems. It's just ax squared plus ay squared gives me that hypotenuse. Okay. So adding vectors algebraically now boils down to finding their x and y components, summing all the x components together, and summing all the y components together. Right? Because if I have something that takes me 3 miles east and then the next directions take me another 2 miles east, regardless of how far it takes me north or south, I'm going to end up 3 plus 2, 5 miles east. Right? If the first set of directions at the same time took me 7 miles north, and the next set of directions only took me 2 miles north, in the end, it's 7 plus 2, and it doesn't matter how far I was traveling east at the same time. Right? So we take the components, and we just add the components straight up. Right? And then we use r squared. R is equal to rx squared plus ry squared. Okay. And we use the inverse. Yes.
Then, if we did this one plus this one, and then we take the square root, we're going to end up with 65.
Let me see. So, actually, you don't even need to do that, right? Just remember, we're trying to find.
The 4 and 7.
So you're talking about just about the 4 and 7 one.
Yeah.
Right. So think about this. So you figure out how far you end up compared to where you start.